For my discussion 3 video, I'm going to be doing Lebl problem 1.5.101. It's a Bernoulli substitution problem. And the question asks to solve the differential equation xy prime plus y squared equals 0 for the initial condition y of 1 is equal to 2. Before we start, let's remember that the Bernoulli form of an equation is such that y prime plus p of xy is equal to q of x times y to the n. For any power n, we can make this equation into a linear equation and solve from there. If n is 0 or 1, the equation's already linear, so we don't have to worry about it. For this equation, we're going to have to manipulate it first to get into this form. So let's rewrite the equation in differential notation, dy dx, x dy dx because of that x in front, plus y squared is equal to 0. Quickly, we can divide this x out, and we'll find dy dx plus 1 over xy plus 1 over xy squared is equal to 0. And to get it into Bernoulli form already, we can do dy dx plus 1 over xy. We're going to subtract this 1 over xy squared from both sides to get is equal to 1 over xy squared. Now, in a Bernoulli substitution, after getting it into Bernoulli form, we're going to divide through by the y to the n power. That y to the n in this case is y squared. So after dividing through, we get y to the negative 2 dy dx plus 1 over x y to the negative 1 is equal to negative 1 over x. Now, we're going to perform our substitution. I'm going to change colors for this part of the process, and we're going to let u equal this middle term, y to the negative 1. That means du dx is equal to negative y to the negative 2. That's the derivative of y to the negative 1 dy dx, because we are deriving implicitly for y. This looks strikingly similar to this first section of the differential equation. So we're just going to say that negative du dx is equal to y to the negative 2 dy dx. All we're doing is multiplying both sides by negative 1. And that gets this to be the exact same as here. And this is still the same as the middle. So we can rewrite this differential equation in terms of u and x. That is going to give us negative du dx plus 1 over x u is equal to negative 1 over x. We're going to instantly rewrite this as du dx minus 1 over x u equals 1 over x. All we're doing again is multiplying times negative 1 to get it into that form. I will rewrite this at the top over here. Du dx minus 1 over x times u equals 1 over x. And that is a linear differential equation. We solve linear differential equations first by defining our integration factor. We do that by taking this middle term of x, changing colors again. We're saying that p of x, not that same p of x, different p of x, hence the little p, is equal to negative 1 over x. That makes mu of x equal to e to the integral of negative 1 over x dx. That's mu of x equals e negative ln of x. And with easy manipulation, we take that negative 1, bring it inside. E to the ln of x and negative 1 simplifies down to 1 over x. So that is our mu of x. Let's rewrite this equation again, but with the integration factor inside, or multiplied into it. 1 over x du dx minus 1 over x squared. 1 over x times 1 over x is 1 over x squared. U is equal to 1 over x squared. We can rewrite this in terms of a derivative, d dx, of 1 over x, our integration factor, times u. If we check real quick, Using the product rule, we take the first term times the derivative of the second term, that's 1 over x times du dx, plus the derivative of the first term. The derivative of 1 over x is negative 1 over x squared. That is, the derivative of x to the negative 1 is negative x to the negative 2 times the second term, u. I'm going to leave a little bit of space, and that is still equal to 1 over x squared. We will integrate both sides with respect to x, dx, dx. This integral and the derivative, they cancel out. 1 over xu, saying they cancel out, but we can really just drop both because the integral of a derivative is just the original. Is equal to, well, the derivative of that 1 got covered up by our integral sign. The derivative of x to the negative 2, the integral of x to the negative 2 is negative 1 over x. And we cannot forget about our constant of integration. We're going to call that c1. Let's multiply the entire equation by x to get u being equal to negative 1 plus c1x. Let us recall that, we'll go with the purple again, u is equal to y to the negative 1. So finally we can be back in terms of only y and x. 1 over y is equal to negative 1 plus c1x. Multiplying by y and dividing by negative 1 plus c1x, we find that y is equal to 1 divided by c1x minus 1. This is our general solution. Sol of the differential equation. I'm going to rewrite this on the next page. We have that y is equal to 1 over c1x minus 1. And we'll recall that our initial condition is that y of 1 is equal to 2. Plugging this in, y as 2 is equal to 1 divided by c1 times 1. That is our x minus 1. We can multiply the bottom on both sides, and we get 2 times c1 minus 2 is equal to 1. 2c1 is equal to 3, and then c1 is equal to 3 halves. That means our particular solution can be written as 1 over c1. That was our general solution. Our particular solution can be written as y equals 1 over 3 halves x minus 1. We can multiply this whole thing by 2 over 2. That's really multiplying by 1. But that allows us to rewrite this as y is equal to 2 over 3x minus 2. We can quickly check that those are the same by going onto the direction field website. We will type in our original differential equation, which was xy prime plus y squared equals 0. That means y prime is equal to negative y minus y squared over x. That allows us to enter it into the website, negative y minus y squared over x. And our general solution being 1 divided by cx minus 1. Just going to change the axes, and we find this is our direction field, and as we vary c, it flows with the arrows. And if we enter 3 over 2 for c, this is our solution. And if we look at 1, we'll allow the x ticks here. 1 is right where 2 is.